Hello! Today I'm going to give a little bit of an introduction on how to use the Google Test Framework along with CMake. So we're going to start off with absolutely nothing except for Visual Studio Code. And I'll show you exactly what extensions I'm using that are important today. I have a lot of extensions, but really the only important ones we need are C, C++, CMake Tools, and that's it. And CMake is a bit of a learning curve, but for this small example, it should be pretty easy to understand and maybe a good introduction to it. We're going to close that off, and we have nothing open yet, so let's open a new folder, and we're going to create a new folder and call it example. All right, select that guy. So first thing you need if you're going to be using Google Test is to clone Google Test. Easy enough. Just open a terminal. And we go to git clone, https, github.com, because if you can tell, I'm totally saying this from memory and not looking at my second monitor. Cloning it from github.com, Google Test. We have Google Test. Now let's establish our project. So the first thing we're going to want to do is create a new file, call it CMake lists.txt. And let's hide the terminal here. So I'm going to sort of type out the basic structure of a component that uses CMake. So first thing I'm going to do, CMake minimum required version, and then you sort of say what version of CMake you depend on. And usually you want to pick the version that you're that you have installed. And you don't get that through the, I don't know if you do, but I don't think you get it through installing the CMake Tools add-on. You may. I'm not sure. I installed CMake separately. You just go to their, you Google search CMake, you go to their website, and you just install the latest version, and you're good to go. What the CMake Tools plugin does is it can detect what CMake you have installed and also what other stuff you have, like I'm going to be using Visual Studio's toolchain to build things, and it kind of helps you set that up. Hopefully if you have the compiler installed and you have CMake installed, everything is pretty much automatic. So we say what version of CMake we need, and I like to have a variable that I set called this, which I'll reuse in multiple places. Actually, in this example, I'll only use it in 2 places, but it's still sort of useful to have. So then if you decide to rename your code, you'll have it in only one place you have to rename. So for the top level CMake, you want to establish the name of the project and also what languages you're using. So the name of the project is first, and then the 2 languages, C and C++. And then we're going to set up some variables that help the build system generator know what versions of the languages, because there are different versions of C and C++. So CMake C standard and CXX standard tell it what versions of C and C++ we're going to be using. And there's one more that I like to set, which is CMake position independent code. I don't know if you really need that, but position independent code is a nice setting to have for libraries that are going to be mixed together and linked together into executables. So we're going to want, at the top level, you're going to want to say this once, enable testing. That tells CMake that you're going to have unit tests. And then we're also going to pull in all our dependencies that are within our workspace. Right now we only have one. So app subdirectory Google test. And then we're going to start describing what we're going to build for our code. So I like to break it up into 2 different variables called headers and source. You don't have to do this, but I like to do this. And then for headers, I like to have 1 line per file name, and we'll just list the headers that we expect to have and the source files we expect to have. Right? And then here's the key line. To actually make code, you either use add library or add executable. Don't quote me on that. It's either add executable or add program. Library means it's going to be linked with other things to form programs. And that's important because when you're running Google Test is going to be your main program. It's going to pull in your code as a library. Actually, that's not exactly true. We're going to split our code into two pieces, the actual code and then the tests that go with the code. The tests that are going to go with the code are going to be a program. The code that's going to be tested is this library. So usually I like to use static link libraries, but you could also make it shared. And here's where you list all your sources and all your headers. So that one statement there should be enough for CMake to make a build system that compiles your example.cpp and makes it into a library. And then because we want to keep our tests separate from our code, we'll put our tests in a subdirectory called test. That's it for that file. So let's go ahead and make the two files we need. So add a file, example.hpp, and add example.cpp. And so this is just standard things you would want to have. So I like to have it for every header file a guard, if not def example hpp, define that header guard, and if. There's a basic structure, right? And the first thing we'll want our example CPP to do is include our header. Fair enough, right? So that's minimal. Oh, wait, hold on. We need to make the test. We need to make the test next. Test next. So test will have its own CMake lists. That's important because add subdirectory, what it does is it goes into that subdirectory and looks for a CMake list there and basically runs that in a child node of the build system. So here's where we're going to describe the tests. So the same kinds of things as the outside. And I'm kind of copying from a recipe over on my other screen here. CMake minimum required, version 3.8, and set this is example tests, and set sources, and we don't really need headers for tests. Okay, so we're going to set the sources up to be, we're going to have our tests in one file called example test.cpp. Okay, then we add executable. So this is similar to the add library, only instead of making a component that's linked into a program, we're actually making the program itself. So we use the name example tests, and we'll pull in the sources. That's all you have to do to describe your end. Now, things that you depend on, you would use target link libraries, and you repeat this, and you say public, meaning it's not just you, but anything using this program would depend on it as well. Oh, I forgot to terminate that. And here's where you're going to list gtest main. That's a target provided by Google Test, which pulls in the main program. So Google Test provides the main program for you. You're linking it in with your tests. And then we need the thing we're testing, of course, example. And then to tell CMake that this program is actually a unit test, we'll run the add test command, tell it the name, and tell it the command to run, which is also the name of the program again. And that's it. And now we just need to establish that example test CPP. So here we'll go. We'll make a new file, example tests.cpp. So minimally, you don't need anything. So with the CMake Tools, yes, CMake Tools extension, you should get, okay, I guess we're not starting with one yet because we need to reload this because we didn't have a CMake list when we started. So what we'll do is we'll tell Visual Studio Code to reload window. When it reloads it and detects that we have a CMake file, it should initialize and say, pick a kit. It'll only do this the first time until you pick one. So it basically detected all of the compilers I have. It knows I have a Cygwin build of Clang, and then we have Visual Studio Community 2017. So let's pick Visual Studio Community 2017. AMD 64 is a 64-bit build, or we can do x86 for 32-bit build. Do the 64-bit one. And it is, unless I made some mistakes, what it'll do is it'll configure a generator, and it defaults to Ninja, which I kind of like. And it'll detect all the tools, and then it's basically building the build system for us right now. And we're done. And it says, do you want CMake Tools to configure IntelliSense? Sure, allow. So now if we hit F7 to build, unless I made a mistake, it should build everything. Okay, so there's a little bit of a warning about the use of libraries. So that's because Google Test is using a different version of the runtime libraries than we default to. So we could fix that if we go, if I remember how to do this right. Under the build directory, so by the way, the name of the build directory depends on what you have set in your preferences. I happen to have set up here for CMake build directory, I have it set to build-VSCode, just to remind myself that I made this build system through VSCode. I think if you don't have this, it defaults to just build or something like that. So build VSCode, and then it'll make a CMake cache. So here, what we're going to look for is, I think it's library. See, I'm learning this along with you. There's something in here that controls whether we're linking statically or dynamically. It's an option in here somewhere. Or actually, would it be, yeah, under gtest, here we go. One of these guys. I'll find it once and then you can just follow along with me and you won't have to find it. There we go. I think it's this force shared CRT. So I think we want to turn this to on. And then when we do, I think it's build, what is it? I think it's under this tab here. We can do clean rebuild, and we should see it. We should make sure that that warning goes away. Sometimes you get these random errors, but I kind of just ignore them. Cool. So we go through and make sure we didn't get any warnings. That's essential. You don't want to have any warnings or errors. And I should also show up in problems here. There are no problems. Great. So when we run this, which we can run if we click on, there should be a tab here. Actually, if there's no tab at the bottom, you can just, again, Control-Shift-P to get the command palette and look for C-test or CMake run tests. There we go. It'll run our test for us, and now it pops up something here where we can click it again whenever we want to rerun our tests. So it passes because we have no tests. Everything passes. Great. So let's make some tests. This is standard test-driven development stuff. So Google Test lets you make really basic tests. Test. We have to give the suite of tests a name, so we can call it anything we want. Let's just call it example tests to be. It doesn't have to match the name of the file, but I generally do make it match, just so it's consistent. And we have to give the actual test a name. So let's just show an example. Just demonstrate G-test macros. Okay. And then here are some basic macros you can do. Oh, hold on. Before this to make sense to the compiler, we need to include G-test, or Google. And let me see if I can get this right. Google G-test / gtest.h. Yes. So it'll find the header because in our CMake lists, we told it that we want a G-test main to be linked into our program. So that not only links it in when we build it, it also is a clue to IntelliSense and the compiler about where to find header files, like gtest, gtest.h. All right, so some simple macros you can do. Some sanity checking. Expect true, true. And then we can run that. Just hit F7, run the test again, still passing. Now, if we were to say false here, oops, if I could spell it right. Doing it live here. Only doing minimal editing to this video. Otherwise, it's just like I'm streaming. Now when we run the test, we see it fails. And it should also print out exactly what line number it failed on. And it'll say the actual value was false, the expected was true. So here's an example, like we could repeat this a couple times. And we'll get 3 of those markers when we run the tests. I'll make this bigger so you can see. So lines 4, 5, and 6. Now, if I were to use Assert, Assert is a more strict version of expect, it says if we don't pass that line, don't continue. So now when I run this, we can see that it only flagged lines 4 and 5 because the assert, it failed, and so it doesn't even get to line 6. You would do this if you wanted to stop a test early, like if there's no sense in continuing, or it might crash the test to continue running because some condition isn't right for you to continue checking. That's where you'd use an assert. So there are lots of variations to these macros. You can, instead of saying expect true, you could say expect equals true, and then some variable, or you can just say true, right? True is equal to true, right? And we can try it both ways. We can say false is true. Dismiss that. So we can see that line 5 says these values are expected to be equal. And by convention, I usually put the expected value first and then the actual value. So if we were checking to see if a function returned a certain value, we would say something like const bool result equals some function f, and then we will put the result here as the actual, right? This is just to demonstrate if we had a function f that returned something, it might do that. And then you'll see it's slightly different. It'll say result, which is false. So kind of, it tells you that it expects true and result to be equal, and the actual value of result, which is false. So we could fix it like by turning that to true. Now it should pass, right? Cool. I don't know why it's complaining about Dart configuration, but we'll ignore that for now. I think that has to do with some part of the C test. And yeah, I don't remember. It's not important to this tutorial. Anyway, that's basically it. You could look at Google Test's webpage here for, they have more documentation. They have a Google Test Primer, which is really nice to look at. And they kind of go through what are the philosophies and basic concepts, and here they list the kinds of things you can assert. So I went over true, and there's also false, and I did equal. There's also not equal, less than equal, greater than equal, etc., etc. So they're all different variations, and there's string versions of it. It gets pretty elaborate. One thing I like to do sometimes is, let's say f is a esoteric function, and just simply printing the result won't really tell us what's going on. But if we wanted to print additional information if it failed, this is how you would do it. You take advantage of the fact that there are operators defined by Google Test for shifting left. Whatever you shift left, whether it's a string, an object, a number, gets printed on the line when the test fails. So if let's make this fail again. Actually, let's make it fail, and we'll just say simply hello world. When we run this test now, not only does it show us the failure, it also prints out whatever we had here. So if we had something like, if we made this an int, and we had it return 42, and if we wanted to get the result and we expected it to equal 16, hold on, it's usually used for side effects we can't observe. So let's leave it bool, and we'll have a global variable. This is bad, but just for illustration, make a global variable called side effect 42, and we'll have it make a side effect change, right? And we'll say if it fails, we'll print. If we wanted to see what the value of side effect was, equals, and then we'll just simply shift it out. It's a bit like the C++ stream operators. So now when we run it, it actually prints out the actual value. So that's useful, like this is illustrating, to print out side effects. Things that aren't directly observable in the assertion, we can print later. Another useful place where you might have this is if this was in a loop, like for int I is 0 to 16, for example, and you wanted to run this, you might print out that it failed in something like that, so you know which iteration of the loop it failed on, for example. All right, so enough of this. This is just demonstrating the macros. Let's actually build up a component. So what I like to do is start with the unit use case. So let's say our example is dealing with computing a multiply and accumulate, otherwise called an MAC. So let's see. Multiply, accumulate, MAC test. Let's just call it MAC. So if we have a MAC function, let's set up some variables. So int x equals 42, int y equals 16, and int sum is 100. So what we would expect, what do we expect when we were to, if we were to call MAC with x and y and the sum? We would expect that to be equal to x sum plus x times y, right? And then furthermore, we would expect, if we were to record the old sum is the sum, actually we should say that here, we should expect that the sum is equal to this. Because the part of accumulate is that we're adding to that sum. So here's a typical use case. So multiply, accumulate. We expect the multiply, accumulate to take two numbers and multiply them and add them to a sum, and then also store the sum back into sum. So first we expect the return value is equal to the old sum plus the x times y. Then we have another assumption that that same value be what's stored back into sum. We could simplify this and say int expected new sum is that removes some repetition. So anyway, now our test case is set up. How do we actually get this to build? It's not building because MAC is unidentified. So we expect that to be in the thing that we're testing. So that would be one directory up. Example.hpp should define it, right? So let's collapse the build directory. So let's go to the example HPP and define it. So int mac, int x, int y, int reference sum. Now you can see that, hold on, what's wrong with this one? Oh, forgot a comma. Now you can see it will build, or at least compile, but it won't link. Because it says it's unresolved. We haven't given a body to Mac. Let's do that next. See, you can see how TDD is kind of designed backwards. You design it from the test backwards. So the first thing we can do is simply do nothing, do the wrong thing, and that should build, but it won't pass our tests. We can see we expected 722, and we got 0. So we can, let's fix it. The naive approach would be simply to return sum plus x times y. That should pass one of the tests, but not the other. It passes the one from line 11, but it doesn't pass the one here on, I guess it doesn't pass this second one because we didn't actually do the accumulate part. So we pass that by changing this around a little and say sum plus equals return sum. Now we should pass our tests. And that's basically how it goes. So you would continue building up tests by just simply adding more macros here. So we could say we could have another test. How about test square? We'll have another function called square. Int x equals 5. Int expected square equals x times x. And then we'll expect equal expected square for square x. And it doesn't compile because square doesn't exist. We have to add it here. Int square. Now it's going to compile but not link because we had to make a definition for it. We'll do that here. And we can have it initially do the wrong thing. Doesn't matter what we do wrong, because we want to see the test fail at first. And it fails, indeed. It should have been 25, but it's actually 5, so then we fix it to do the correct thing. Run it again and our test should pass. Yay! Okay. So what do you do when your tests get more and more involved? Let's say you had a lot of tests that had the same kind of setup. Well, there's something called a fixture which you can employ. A fixture is just simply a structure or a class. I like to make it a structure just because you don't need to encapsulate anything, because we're all friends here in the same module. And you name the structure the same as what you've been naming your tests. Only it's going to inherit from a special class called testing test. If I get this right, is it test? Is it yeah, right. The IntelliSense is helping me out. It's uppercase TST. So what that gives you, if we look at that class really quick, you gonna help me, IntelliSense? There we go. It gives you a bunch of convenience things. Two that I use most often are these setup and teardown. So they're virtual functions. We can override them. We can do something like this. It's they're both void. Virtual void setup, right? Override. I don't always remember to say override. Some compilers will give you a warning if you don't, because they are virtual. And tear down, right? Yes. So you can do whatever you want in here. So for example, if I wanted to, I could have a variable, and the setup might be to initialize that, 42. And a tear down, we could do other things like if we allocated memory. Let's allocate some memory here. This is a horrible thing to do, but we could do this. And we just remember to always delete X here. Then in the way you would use this fixture in tests is simply add _f. Now each one of these tests is not only a function, it's also in a sense a subclass. So you have access to X directly. So we can remove our local X here and our local X here, and then simply I could do this, but it might be hard to read. So what if we made a convenience function and we call it get X, return X, right? Now we can say get X wherever we have this construct, get X. There, there, and there. And there, and there. Cool. Run that. Stuff's still passing. And you could even do things like this. Printf, hello world. Now whenever our tests run. Oh, that's right. I forgot to say, if tests pass, you won't actually see standard output. So we're not going to see that. Never mind. Anyway, you get the idea. I think if we did the standard error, we actually might see something. Yes, no, maybe so. No. Anyway, I bet if I run it on the terminal, I'd see it. So it's going to be build example test. Test example test. There we go. So we see it on the terminal. We don't see it in the test summary here because the test didn't fail. So any kind of things you want to do in setup and teardown, you could do it here. So I could say starting up. You get the idea. I might be kind of belaboring the point. Build that guy. Run the test again. Starting up, tearing down. Interesting thing is it only tells you the result of the test after we're done tearing down. It's kind of nice. All the output for a run is nicely bracketed like that. So hope that gives you a basic idea on how to set up tests with Google Test, with fixtures, and what you could do with common variables and functions, helpers, set up and tear down, and how we break our tests up into individual cases, how they're run. A couple of other points. If you wanted to, you could rename this and take it out of the fixture, add back in an X, Now when we run it, we'll see something a little bit interesting. On the terminal, actually. You'll see it gets broken up into two different sections. They call them cases. That's useful if you, usually I do this when I have two different classes I want to test. I usually put them in two different Test Cpp files, but you can do it in the same one like I did here. Because the names of these tests are different, they go into different test cases, and they have different bracketed sections. It's also handy for if you wanted to only run tests, a certain test case, you could have a filter that starts with example test2 star, and it'll only run that second test case. You can do any kind of regular expressions here as well. So I could say star Mac, and it runs the Mac test, or star square runs the square test. So there's lots of other options you can get to gtest, and there are lots of other macros you can use with gtest. So I totally recommend looking at their test primer, which you can get to from their Git page, and learn all the things you might find useful. So anyway, I hope that helped out, and you got to see a little bit about Google Test and CMake, and hope you'll watch me on Twitch, and see you again soon. Thanks, guys.